Section 6.2 Kirchhoff laws. There are two Kirchhoff laws, the Kirchhoff current law and the Kirchhoff voltage law. Together is called the Kirchhoff laws. Kirchhoff laws together is a handy method. We use them to apply for a complex circuit to figure out the voltage drops on every quantities and also the current in each branch. A complex circuit means a circuit has more than one loop, such as a circuit like this. Of course, Kirchhoff laws can still be used to figure out a simple circuit, which is a circuit that has only one loop. The order of the laws is not important. We can study the Kirchhoff current law, KCL, or Kirchhoff voltage law, KVL. So how about let's begin with learning KCL, the Kirchhoff's current law. The picture here shows the Kirchhoff current law. The box to the left shows all the branches bring the current into that junction node in the middle. After the current enters into the node, the current will leave that node and entering to the box to the right. And as you can see, that box is labeled as output. Those are the output branches. The Kirchhoff current law states all the currents entering to a node must be the same amount of current leaving that node. It is not like 1 ampere entering to the node and then 2 ampere comes out. Where's that extra current come from? Or it's not like 2 amperes entering to the node, but at the end only 1 ampere coming out from the node. So where's the missing 1 ampere? Maybe one analogy is like a person drinks 1 liter of water. Eventually, that 1 liter of water should come out from the body. Well, you get the point. If you want to express this relationship in mathematical expression, the equation below shows the relationship. As you can see, the I in, which means the input current, so I in 1 is the input current in branch 1, plus the input current of branch 2, plus the current in branch 3 all the way to the last branch. That amount of current add up together should equal to all the current coming out from the node, which is the total current among all the output branches. That is I out 1 plus I out 2 plus I out 3 plus I out m. M and n, they are different numbers, which means the number of input branches may be different from the number of output branches. But the current should be the same. The amount of input current is same amount of the output current. So let's use a different picture to describe the same thing, the Kirchhoff current law. Here, the blue branches indicate these are the input branches. Those wires bring the current into the node, and the orange wires means the current coming out from those branches. The total current entering into the node should be same amount of current leaving the same node. And as you can see, we have the same expression here. Here has another analogy. It's the water pipeline system. Let's just focus at this region of the system. The big arrow indicates the water entering through this pipe. The 2 arrows, the up and the down arrows, indicate the water coming out from the T-shaped coupling connector. For example, if we pour 1 bucket of water into the main pipe, the pipe on the left-hand side, we expect to see the same amount of water coming out from the little pipes on the right-hand side of the connector. If less water come out, we'll be surprised. We'll be even more surprised if more water come out from that connector. How about let's work on this example. So here, like a spider web, a node is in the center of the circuit. and there are wires bring the current into the node, and there are wires bring the current out from the node, which means there are input wires and the output wires. The direction of the arrows shows the kind of wires. How about let's color code those wires? So I use blue color indicate the input wires, and the orange color indicate those are output wires. How about let's begin at here. I just randomly pick one wire. So this is 4 ampere. Added to the node, right? It brings the current into the node. So 4 ampere plus 3 ampere plus 5 ampere plus 7 ampere and plus the 11 ampere. These together is the total current entering to the node. Equals to, but now let's take care of the current leaving that node. So I can pick this branch first. That is 6 ampere plus 3 ampere and added to this unknown current I. So we have all this bunch of numbers and one unknown variable. We can find the I. The blue numbers are the input current. If we add them up, that is 30 milliamperes. The orange numbers indicate those are the output current, which is 9 milliamperes plus I. We can simply apply algebra to figure out I, and I equals to 21 milliamps. So this is Kirchhoff current law, KCL. Now let's study the second Kirchhoff law, and that is the Kirchhoff's voltage law, or KVL. KVL states for a closed loop, a closed circuit, the total voltage provided by the source equals to the total voltage drops on all the resistors in that closed circuit. If this is confusing, there is another way to look at it. That is, if we add all the voltages in the system, including all the voltage drops and all the source voltages, the net voltage of the system equals to 0 volt. And that is the second expression here. My personal favorite expression is the second one. For example, for a closed circuit, there are n voltages. If we add them up, the sum equals to 0 volt. Let's look at this circuit. This circuit has one source Vs and 3 resistors. They are R1, R2, and R3. The voltages of the 3 resistors are V1, V2, and V3, corresponding to R1, R2, and R3 respectively. Apply KVL. Vs equals to V1 plus V2 plus V3, which means the total voltage provided by the source should equals to all the voltage drops together. Or the source voltage, subtract V1, subtract V2, and subtract V3, that equals to 0. The net voltage of the system equals to 0 volt. Let's take a look at this example. Here has one circuit with one source, Vs equals to 10 volt, and 3 resistors. The voltage drops on R1, the V1 equals to 2 volt. The voltage drops on R3, V3 equals to 5 volt. And we want to find out V2, the voltage drops on R2. So how about now, let's use KVL to set up the equation. Vs, the 10 volt, subtract V1, subtract V2, and subtract V3. The net voltage of the system equals to 0 volt. And then let's apply algebra to rearrange the equation. So it's the equation for V2. After rearranging the equation, right, we move V2 to the left. So V2 equals to 10 volt, subtract V1 and subtract V3. Next, substitute the numbers into V1 and V3. So V2 is 10 volt, minus 2 volt, and minus 5 volt. Therefore, V2 equals to 3 volt.